All right, so now it's recording. Let's hope it works. Now, again, please let me know if you're unable to see my screen, if you have trouble. I hope this works better than Blackboard, but let's try to make it work until 9:40, right? We already lost a lot of time. So I was telling you guys about what is an ordinary differential equation and what a partial differential equation is, okay? So we wrote down an example for an ordinary differential equation. Now let me give you an example of a partial differential equation. So a partial differential equation, you can think of it as, say, partial u, partial t, plus t squared is equal to partial square u over partial x squared. Now, this is considered a partial differential equation because you have two independent variables, which happens to be t and x, okay? So any questions on these two definitions? All right. So just want to make sure you guys are able to see my screen so far.
Yep.
Okay, great, awesome, thanks. Okay, so the next way we can classify a differential equation is by looking at its order, okay? So we have to define what is an order. So, oh, no, not typing. So what's an order of a differential equation? Well, an order is pretty much the highest power that appears in the derivative of the derivative, okay? So the order of a differential equation is the highest, oh my God, no, highest. It's the highest derivative that appears in the equation. So that's what an order is. Now, let me give you an example of this, how you can identify what the order of a differential equation is. So, for instance, say you have, say y to the third derivative plus y to the fourth derivative is equal to 3t squared. So what will be the order of this differential equation? So you're looking at the highest derivative that appears in the equation. So the highest derivative would be this term, right? Because it has the fourth derivative. So the order is going to be a fourth order. So that's how you can classify them, by looking at the order. Now, the next thing that we're going to talk about to classify them is by looking at if the equation is linear or nonlinear, okay? So I'll give you the definition of what a linear equation is, and then the opposite will be the definition of nonlinear, okay? So you don't have to really know definition for both. So let's write down, what does it mean for a differential equation to be linear in the y variable, okay? So that's the key idea. So a linear differential equation has the form, so it must be written in this specific form. So you have a function of the independent variable, say t. Now, usually we use t or x for the independent variable, and y, u, those are the dependent variable. Most common notation. but you could see different notation depending on the text you're reading, okay? So in this case, t is the independent variable, and then you have involving y prime, y double prime, y third derivative, all the way up to, you know, nth derivative equals to some constant k. So if the function happens to be in this form, then that differential equation is linear. So that means, what is it when it's not linear? Well, that means not linear, it's going to be of the form any combination of these, okay? So for instance, say you have y times y prime plus xy squared is equal to sine of x. Now that's going to be considered, oh, sorry. Now that's going to be considered not linear because you have this term right here. And you also have y squared right here. Because of those two terms, it doesn't fit into this definition we have. So we call this equation a nonlinear differential equation. Does that make sense so far? Maybe, not really.
Professor?
Yeah.
Why does this not match the linear form?
Well, this one doesn't match the linear form because you have the following. You have this guy right here, which doesn't appear in our form right here. You see that? You have y times y prime, which we don't have it in the form. So that's why it's nonlinear.
Okay, got it. Thanks.
So really the quick way to remember this, or the best way, I think, is that all the terms that involves y, y prime, y second derivative, anything that involves y doesn't get played around with it. Like you don't modify the function y. So you can think of it that way. So for instance, if I have, say, e to the y, so I'm taking my dependent variable y and I'm doing exponential to it. That makes it nonlinear. For example, if I do ln of y, that's also nonlinear. If I do y times y prime, that's nonlinear because I'm modifying my dependent variable. So if you play around with your dependent variable, then that's considered nonlinear. Okay? Or you can think of a square root of y. If you see that, that's also nonlinear. Any questions on this? Okay. All right, so let me give you a couple examples, and you're just gonna classify them based on if it's a linear equation or what is the order of the equation, and if it's a PDE or ODE, okay? So just classify them and see how you perform. So here are a few examples. So here is one. Say you have dy dx plus sine of y is equal to tangent of x. So I want you to tell me if this is an ordinary or a partial differential equation, what is the order of the equation, and if it's linear or nonlinear. So 4 things you're jotting down for this equation. And the second example I have for you, it's going to be, oops. So here we go. So same instruction for 2 as well. And then the third one, Okay, so here are three equations. I want you to write down if it's an ODE or if it's a PDE, and then the order. What is the order? And then the last thing you're going to write down, linear or not. If it's linear or nonlinear. So go ahead and do that. I'll give you, say, about a minute, and that should be enough to classify these problems. Just put that on the side. Okay, so so it should be enough time for you to answer these three problems. So can someone tell me what do you have for the first equation?
I found that it was a partial differential equation
Okay, so why do you think it's partial?
because it's in terms of y and x.
Well, so for partial, right, we have to have more than one independent variable,
Oh,
right? So for example, this one that I gave you, right, we have two independent variable, which is t and x. Now, you're always going to have one dependent variable because the dependent variable is always one. You can't have more than one dependent variable. It doesn't make sense.
right.
So you're always looking at the independent variable. Is it one or is it more than one?
I see.
Okay, right. But good point, right? So this is the time you want to make mistake because that's the only way we can learn. So I'm glad you mentioned this. So do we agree that the first one is an ODE?
Yeah.
Right? It's one independent variable, which is x only. Y is the dependent variable. So so it's an ODE. Now, what's the order of this equation?
That'd be first order.
Yeah. Because the highest derivative we see is 1. And then is it linear or nonlinear?
So for the, I actually had a question about this. For the, would it be linear because there's no like y derivatives that are attached to anything? It's just y on its own. That's
All right, so this term is check. This term is fine. Now, this is sine of y. So it's like you're inputting your dependent variable into sine. So you're kind of playing around with the dependent variable. So you see how I said it here, that all of these terms, oh, I forgot the y, sorry.
okay. Yeah. All right. That makes more sense. Thank you.
Right? So all of these terms has to be totally independent. You cannot multiply them. You cannot raise them to a power. You cannot put them into a function because that way it'll become nonlinear. So because you're doing sine y, so your dependent variable becomes an input for the sine function, that makes it a nonlinear. Okay. So I hope this makes sense. Let me know if you have questions. Okay, moving on to the next one. Now, can someone else tell us what do you have for the second one?
It's a first order.
Mm-hmm.
It's nonlinear.
Okay, why is it nonlinear?
Because the y variable is messed around with. You're multiplying x on one of the terms, and then you're squaring in another term, the y prime.
Mm-hmm. Well, this is fine because it's multiplication, but the
Oh,
trouble
okay.
is this one, because you're taking the dependent variable, its derivative, and you're raising it to some power. So that makes it nonlinear. But for the second term, if I had, say, for instance, y times y something, or y times y to the, say, second derivative, that will make it a nonlinear as well. But we don't
What if
have
it was
that.
just y times y?
That will still be nonlinear because you would be y square.
Okay.
Mm-hmm. Yep, you got it.
So multiplication is fine, but exponents make it nonlinear?
Multiplication with the independent variable is fine.
Oh, okay, okay.
Yeah.
But what about if it was a constant? Same thing?
That would be fine.
Okay. And I said it was a ODE.
Yes, ODE. Okay. Yep, that's also correct. So any question on the second example?
Can you explain why it's not second order?
So it's not second order because the derivative we see it on the equation is this guy right here. It's only a first derivative. This is just a power to the derivative is being raised to a power, which is different from the order, right? Order is the number, the highest derivative you see, which is a first derivative.
Okay, thank you.
Mm-hmm. All right, now what about the third one? What do you guys think?
It's seventh order.
Right, so the order is seventh order because that's the highest derivative we see.
Is it linear?
Mm-hmm. So it's linear, right? This one is good, this one is good. This is also good, so it's linear. Now, is it an ODE or PDE?
It's an ODE.
Right, it's an ODE because we only have one independent variable. All right, so that's right, simple, quick classification, but really important, okay? So make sure you understand these terminologies and you make sure you know how to apply them to examples. So for each definition, I would encourage that you always write down an example next to it so that it clicks quickly, okay? When you see an ODE, well, what's your favorite example? When you see a PDE, what's your favorite example? And then for order, I guess you can write down your favorite example or the one I have here. And then linear and nonlinear, just have the form written down and then write down a few examples that will help you to understand what does it mean to be a linear and what does it mean to be nonlinear, okay? All right, so having said that, let's move on to another concept. Now, like I mentioned earlier, for this course, you're given a differential equation and we're finding the solution most of the time, almost all the time. So we want to know, how do we find the solution? Meaning, what is the function that satisfies the differential equation, right? So before we get into how to solve, that's going to be chapter 2. Now for this subsection, we want to determine, if I give you a function, can you determine if it's a solution or not? Okay, so that's the next subsection we want to focus on. So we want to know how to determine if a function is a solution. Okay, to a differential equation. Oh, okay. So that's the next section we want to talk about. So let me give you an equation, and I will also give you a function. And I want you to tell me, how would you know if that function is a solution? Okay, so that's the next thing we want to do. So suppose you're given the following. You're given t times y prime minus y is equal to t squared. And I want you to show that the function y of t, which is equal to 3t plus t squared, is a solution to the differential equation. So I give you a differential equation, I give you a function, and I want you to show that this is a solution. How would you do that? What do you think? So just take a couple of seconds and think about it. How can you tell something is a solution? Now think about it in algebraic sense. If you have a function, right? So think about it from the past. So I say, okay, y equals x squared, right? And I tell you that show that, let's see, 2 comma 4 is a solution. How would you show that if I give you something like that from algebraic sense? Yeah, right? You just plug it in. I give you a point. I want you to show that this point is a solution. Well, this point is on the parabola, right? Not a solution, what the heck? Show that this is on the parabola. Right, so you'll just plug it in. So in order for me to show that this function is a solution to the given differential equation, well, I need to make sure when I plug this in, it makes the statement true, right? So that means in order for me to plug in, I have to compute its first derivative, because that's what I'm going to plug in here. I have y already that's given, and just manipulate and see both sides are equal to each other, okay? So that's the idea. When you're given a function, you can verify it by simply plugging it in. So you compute its appropriate derivative and see if it works. So I'm going to go ahead and compute its derivatives. So we only need up to first derivative. So y prime is going to be, so just simple power rule, right? So what's the derivative of this? Who can tell me? Right.
3 plus 2t.
Right, 3 plus 2t, right? Something we should all know by now. So I know y prime is this expression. I know y is given to me as that. I just plug everything in. So plug in y and y prime into given equation and see if it makes the statement true. So we have t times y prime, so t times y prime, which is 3 plus 2t. And then we have minus y, which was the given function, that's 3t plus t squared. Remember algebra, don't forget algebra, right? You have to be very careful when you make this substitution. Okay, now I want to check if this is true. Let's go ahead and check. So here I'm going to distribute t, and here I distribute -1. So we have 3t plus 2t squared minus 3t minus t squared. Is that equal to t squared? Right? So it looks like these will cancel out, and then the rest will simplify to just t squared on the left side. That is equal to t squared on the right side. Check. So here's a typical question where you're given a function and you just need to show if it's a solution. You compute its respective derivatives, plug everything in, and then show that the statement is true, okay? If it didn't solve, then we would say it's not a solution. Any questions on something like this? So you will have some of these for homework, so make sure you do them. Some of them could be a little tedious, but everything takes practice. So make sure you practice and then you know how to do this type of problem. Now here's another type of problem you might encounter while you're doing the homework. So this is example 2. So determine the value of R for which the given differential equation has a solution of the form y equals e to the RT. And here's the differential equation. Y prime plus 4y equals to 0. So how would you do something like this? I'll give you a couple of seconds to think and then let me know when you're ready. So anyone has ideas? Just tell me anything, okay? It's okay if you get it wrong. We're all here to learn, okay? So it's okay if you get it wrong. I don't really mind.
We start by taking the derivative first?
Yeah, that's it. Right, so I give you a function, right? I say, okay, I want the solution to be in that form. Well, if I want that to be satisfied, and this is how my equation looks like, which involves a first derivative, okay, so I can just take the first derivative of this guy, plug everything in, and then I can solve for R that will satisfy the equation, okay? So we take its first derivative. So R is a constant, T is the variable. So you have R e to the RT. So I have an expression for Y, I have an expression for Y prime, I plug everything in. And then I can solve for R. So we have now plug in Y and Y prime into the given equation. So you have Y prime, which is R e to the RT, plus 4Y, which is e to the RT, is equal to 0. And now here comes algebra again, right? Every time once we're done doing differentials, you do the algebraic work. So now we factor out the common factor, which is e to the RT. Then you're left with R plus 4 is equal to 0. Well, the exponential can never be 0, right? So that means only R plus 4 has to be 0, which will give us R is equal to -4. So there you go. That's the value for R that will satisfy this differential equation if we assume that the solution form is y equals e to the RT. Any questions on this? Okay, so let's do one more problem before I move on to something else. So here's another example. I want you to determine, whether the function u of tx is equal to e to the -36t sine 2x is a solution to the partial differential equation u sub t is equal to 9uxx. Now, here I give you a partial differential equation. Now, this equation is very well known because we're going to study this equation later on at the end of the semester, almost toward the end, chapter 10 stuff. So this is what we call the heat equation. We're gonna study this in chapter 10. So you will know how to find the solution to this problem. But right now, I just want you to determine whether the function I gave you, which is this guy right here, if that's a solution to the partial differential equation. So what do you guys think? How do I determine if this weird looking function is a solution to this? Now, the notation might be a little weird for you if you're seeing it for the first time. Now, if you took calculus 3, I believe, you did see partial derivatives. Did you guys see partial derivatives? Maybe
Yeah.
a little, okay. Now, do you guys remember how to take partial derivatives?
Yep.
Yep. Okay, great. So as long as you remember how to do that, you're in good shape. If you don't remember, that's fine. Of course, with practice, you're going to build up to it, okay? So I have this function which depends on two variables, t and x. U is the dependent variable. So you can think of u as y, but instead of y, we're writing u. So you have u, which is a function of t and x, is equal to e to the negative 36t and sine of 2x. Now, I want to determine if this function is a solution to this piece right here. Well, that piece involves partial respect to t and a second partial respect to x. So that means I need to compute those partial derivatives, and then I can plug everything in and then do some algebraic work and determine if both sides are equal. So that's the idea with this. So go ahead and take the partial derivatives of u of tx, and then we'll start in just about a couple of seconds. So I'll give you a couple of seconds to write down what you think are the partial derivatives are. Okay, so let me show you how to take partial derivatives, but if you do remember it, you can compare your answers with mine. So if I want to take partial of u respect to t, well, I know x is going to be treated as a constant. So anything that involves x is a constant. So that means this guy is a constant, okay? So I'm only differentiating e to the negative 36t, which is negative 36 e to the negative 36t, and sine 2x is treated as a constant. So that's my partial respect to t. I hope you guys are okay with that. Let me know if you have questions. Let me erase that. Okay, now for the second part, I need to take the partial of u respect to x twice. So I'm going to go through the partial respect to x first, and then take its derivative second time. That will give me the partial of xx. So let's go ahead and take partial of u respect to x. So that would give us, now we're going to treat this as a constant because that involves t variable, not x. We treat that as a constant, so that's e to the negative 36t. Now what's the derivative of sine 2x? So 2 cosine 2x. Great, so hopefully you remember, you guys all remember your product rule and all those quotient rule, all those, you know, fun stuff from calculus. Take them over here and then have fun with them. Now we're going to take the second partial of this. So I want to find uxx. Again, e to the negative 36t is treated as a constant. So I'm only differentiating the cosine term. So this is a negative 4 e to the negative 36t sine of 2x. So that's my second partial with respect to x. So I have my expression for u sub t, and I have my expression for u sub xx. And now I plug these into the differential equation and test if both sides are equal to each other. Any questions up to here? Okay, so continuing from here. So now let's plug in u sub t, u sub xx into given differential equation. So we get, so my differential equation is u sub t equals 9 uxx. So that's going to give us the following. So we have u sub t, which is negative 36 e to the negative 36t, 36t sine of 2x. I want to know if that's equal to 9 times u sub xx. So that's 9 times negative 4 e to the negative 36t where am I up to? Sine of 2x. So that's the setup I have when I plug these partials into the equation. Now the left-hand side is already simplified. There is nothing to do. But the right-hand side, we can multiply 9 to the input. Will be negative 36 e to the negative 36t sine 2x. Now, is it equal to each other? Yes. The left side is equal to the right side. Hence, this is the solution to the PDE we have here. So let's check. So sometime you'll be testing partial differential equation. Sometime you'll be testing just an ordinary differential equation. But the idea is the same. You take its respective derivatives, plug everything in, do the algebraic work, and show that the statement is true on both sides. And if it's not true, that means that function is not a solution to the differential equation. So that's the takeaway from this section. Any questions? All right, so moving on from here. So the next section we're gonna start with is chapter 2. So in chapter 2, I'm going to rearrange the sections a little bit. So we're not gonna start immediately with 2.1. We're gonna start with 2.2. And then we're gonna go back to 2.1 and then blah, blah, blah. Okay, I'll fill in as I go in. So chapter 2, we're going to start with, well, chapter 2, let me just give you the heading. What does it call? We're going to be solving first order differential equations. So that's chapter 2 is about. You're going to learn 4 methods on how to solve first order differential equations. So there are going to be 4 different methods to solve them. We're going to start with 2.2 because in my opinion, I think it's one of the simplest method. So why not, right? And I like to call that method 1 because it's very quick to check and it's pretty fun. They're all fun. This is just quick and I think you can manage that when you're seeing it for the first time. So we're going to start with 2.2 and we're going to learn the method called separation of variables. So this is called separable equations. And the method we're going to use, it's called separation of variables. So let's label this one method number 1. Okay? And then as we go along, I'll write down the methods for you. Now, how does this method work? Well, we're only working with first order, so we will have equation of the following form. So your equation will only have the first derivative. So you will have either dy dx equals to some function of x, y, where x is the independent variable, y, as usual, the dependent variable. Or you might also see the function written in this form, y prime is equal to a function of f of xy. Okay, so any of these form will be displayed to you. It's either dy dx or y prime. So be familiar with both notations. Now the solution to this equation, so the solution to this equation is y of x equals blah, blah, blah. Something like that. Okay, so you're looking for a function of x that will solve the differential equation. So you're giving the derivative and you're going backwards to figure out what is the function that will solve the differential equation. Okay, so how do we do this? Well, here's how I'm going to illustrate the method to you. Okay, so this is called the separation of variables. And we're calling this method number 1. So first thing first is, if the differential equation is separable, then you should be able to write it in this form. Separable meaning you're able to isolate the x variable and y variable into 2 different terms or in 2 different sides. Okay, so one, if the ODE is separable, which means you can write a function of x with its partial x and a function of y, let me call it g, of y with its partial y is equal to either 0 or a constant. Okay, something like that. You're able to put its differential with the functions variable. If that is the case, then use the method separation of variables. What is that method? I will illustrate in just a couple of seconds. Once we do that, we integrate both sides. Okay, and once you integrate both sides, you are going to have your solution, and you can write the solution in 2 different forms. So you can write the solution in either explicit form or implicit. Explicit means you're able to solve for y. And implicit means x and y are all together. It doesn't matter. But explicit means you're able to say y is equal to blah, okay? Let me give you the first example and then I'll illustrate this method. So here's our first example for this. So say I want to find the solution to the following. So here's the first example. So let's solve the differential equation. Let's say dy dx is equal to 2x. And I claim that this equation is separable, which means I want to write a function of x with dx, and I want to write function of y with dy. It could be in either side, okay? But the idea is really you're able to separate them, and then you can integrate both sides with its respective variable. So I can multiply both sides by dx, right? So I have dy is equal to, oh boy, no, okay, is equal to 2x dx. So that's separated. Do you guys see that it is separated? It's the method separation of variable applicable to this equation. Kind of. So here I have a function of y. Here I have a function of x tagged with its differentials. Well, now that I have separated the variables, I can go ahead and integrate both sides. So let's go ahead and integrate both sides. Integrate the left-hand side. So on the left side, you're just integrating 1 respect to dy. On the right-hand side, you're integrating 2x respect to dx. What's the integral of 1 respect to y?
Y.
Right? And then integral of 2x respect to x?
X squared.
Right, so this is x squared. And we need a constant, right? Because every time you integrate, there's a constant that comes out. Now, you might wonder, well, on the left-hand side, we also have a plus c, and the right-hand side, we also have a plus c, right? Because you integrated both sides. But you don't need too many constants flowing around. You can just combine the left side constant with the right-hand side constant and just call it a c, you know, just one c. You don't need 2 of them. So I can just eliminate this one. So let me go ahead and do that. And that's okay. So our solution is simply this function right here. That is our solution to this differential equation. So you see how we have a function that involves derivative, and then we're able to do some, you know, fun stuff. We're able to get a function. When we actually take its derivative, we get back what we started with. So that's the cool thing about this. You can always check that you have the right answer by computing its derivatives, okay? So any questions up to here? All right, so we're going to stop here. It's 9:40, so it's time to go home. Well, you are home, but it's time to go, right? So I'm going to stop right here. So let me just do that.
I have one quick question.
Sure.
How can we tell if it's separable